Acceleration is body's rate of change in momentum in proportion to the size of the force applied, travelling in the direction of the force applied. So this can be as simple as a player making a run up prior to a layup or sprinting quickly down the wing. And obviously the speed at which they'll do this is dependent on the amount of force they apply against the ground, and they'll travel in the direction that the force is applied. And then lastly is N3, Newton's third law of reaction, which states that for every action force applied there is an equal and opposite reaction. So a good example of this would be the reaction between the foot and floor in takeoff for a layup, or between the ball and hand when blocking a shot. So between, say, the ball and hand, the ball will apply as much force to the hand as the hand applies to the ball, and with the foot and floor, the floor will apply back as much force as the foot does to it. So stability and instability. So stability is the ability of a body to resist motion and remain at rest, or to withstand a force and return to its original position without damage. Stability is relevant to the centre of mass within a player, and centre of mass is the point at which a body is balanced in all directions, the point from which weight appears to act. So centre of mass is typically located around the belly button of a person, if not just above or below, and it can be easily manipulated. The line of gravity runs directly through the centre of mass, and height often determines how far the centre of mass is from the ground, which is typically why taller people often have poorer balance. The base of support is quite relevant in sport, as it typically determines how stable a person is when performing certain skills. The more points of contact there are, the more stable a person is, so this could be hands and feet on the ground. And also the lower and wider the individual is, their stance is, the better. So with points of contact, it could be a case of being on one foot makes you very easy to knock over, as your line of gravity is very easy to move out of line. Whereas if you had, say, 2 feet wide spread and a hand on the floor, you'd be very stable, as your centre of gravity, your line of gravity would be very low to the ground, and in between the base of support. So in the box out and rebound, we see this in that players typically get very low and wide with their feet around their opponent to prevent them being shoved off or pushed over, and to not allow the opponent to get around them very easily. This ensures that someone will stay stable, as it's crucial to have in order to increase stability as such, have a lower centre of mass. You want to keep the line of gravity within the base of support by having a sturdy, straight body shape. You want to be able to widen the base of support and maximise the points of contact with the ground. So here we just see a picture of our individual on the force plate. So obviously here it's jumping. It would be better if you could see the whole body, but essentially we've got the key part of them actually taking off from the ground, just being recorded here on a phone. Obviously we've got the camera here. It's being analysed over here by this jump plate. So these are some of the results from the force plate. So here we can see that we've got our best performer, our subject, and the group mean here. So overall time in air for our individual was actually below the group mean. It was quite far from the best in the group. And it was lower than the group mean, which is quite poor. It means they were unable to essentially get themselves high enough to have a long time in the air. Resultant force, so the total amount of force actually applied in newtons, our subject got just over the group mean, not massively so, but was substantially below the best in the group still, which means there's definitely stuff to work on here to get them to the same level as the best in the group. And obviously, of course, with the best in the group, it's not proportionate to elite athletes. Elite athletes would be getting much higher scores than the best of the group. So, if anything, these subjects can go even higher than this point. They could be coming right up to well over 1,000 newtons. Mean power output in watts, you can see just above group average still. Still quite far below the best in the group, as we can see here. But not necessarily bad for this level, but once again could be a lot higher for an elite athlete. Impulse overall was actually quite low, lower than the group mean, quite a bit lower than our best in the group, meaning potentially that it took too long, possibly, for the individual. So impulse isn't quite the same level as everybody else. Here we see the sort of linear motion based thing, so acceleration was quite good for our individual. They were quite high compared to the best and group mean, so essentially putting them quite high up in the group, but still not as good as the elite performer. And mean velocity, velocity obviously being quite important in gaining jump height, as the higher your velocity of takeoff, the higher you'll get, was lower than the group mean substantially, and a fair bit lower than the best in the group, and obviously substantially low compared to our potentially our elite athletes. And this is the most important one here, essentially, as this will be properly analysed in 6.4, but their overall jump height was lower than the group mean and much lower than our best in the group, which definitely means it's much, much lower than any elite athlete would get, especially with all of these results in this position. The small forward, they want to be getting very good jump heights, they want to be able to produce lots of power, lots of force, just simply due to the fact that they'll need to do it quite regularly. They need to be able to get very high up in the air, move around a lot quicker, and just generally be around the court a lot more and be able to jump higher to block, layups, shooting, box out and rebound would be much better if they could jump a lot higher, so they'll be able to take the ball from a higher point. So overall, the individual does need a lot of work doing to, in the end, increase overall jump height by increasing these smaller factors. So all in all, the numerical model is good in the sense that you can use it to develop technique or physiological adaptations. So yeah, you're able to, you can see where maybe a technique's gone wrong or where it's not quite working for them, or say their overall force output's quite bad. This might be how you go, so this is why your jump height's bad, to work on. It's very good for tracking change, as it can be very easy turned into a graph to see changing jump heights, changing power outputs, changing acceleration, everything. The software gathers very precise data, is very useful, and can be compared across a wide range of different athletes. However, of course, the problems with it are that it is very elitist, it's very hard to get access to. It's a specialist facility, essentially. You need good knowledge of the technology and how to actually read the data in order for it to be useful. When we've done it, it had quite low ecological validity, as there was a lack of realism to the actual skill. You'd most likely be running a lot more before jumping in basketball. You'd be in a court, you'd have other opponents around you, lots more factors than simply standing in a room and jumping. You need to know all the joint axes, and obviously with the cameras for the 2D imagery. Autofocus often struggles with motion, so you might not get focus on images and recordings, meaning they could be quite poor. There needed to be something to ensure a standardised jump angle, which we didn't have, so essentially it could have been that you set them at the 135 degrees, but then they dropped before actually jumping to, say, 130, or maybe extended slightly to up to 140. So overall, it's oh, and of course there's a degree of subjectivity in the starting points of phases, because it's done a lot by someone's eye. They have to be able to determine which bit's which on the graph, as it obviously doesn't tell them. So once again, you need to know how to read the data, and it can be a very time-consuming process. So overall, it's very effective in gaining very elitist data and precise data, but it doesn't come without its disadvantages. And that is the end of 6.3.